In this paper, we present an approach to learning unsupervised forward models for robotic pushing manipulation. How can we come up with a sequence of pushing actions to achieve a goal configuration using visual observations? In model-based planning, we can find the action sequence by performing forward prediction. Most existing learning-based forward prediction approaches formulate the forward model by factorizing the scene image into object instances. This is achieved by assuming access to ground truth information such as object position, bounding box, and mask. We identified two major limitations in the existing work. First, the proposed forward models heavily rely on ground truth information. However, obtaining the ground truth object states is not always feasible in practice, especially in real-world settings. Second, factorizing the scene into the underlying object instances implies hard-coding the number of objects in the formulation. This limits the generalizability as it requires the forward model to be retrained from scratch based on the number of objects in the scene. To address the limitations of the existing approaches in forward modeling, we propose KINet, Keypoint Interaction Network. Our proposed framework performs unsupervised forward modeling using raw RGB images and does not rely on ground truth state information. In addition, our framework performs forward prediction in a lower dimensional keypoint space and therefore is generalizable to a variety of unseen circumstances. Using RGB image of the scene, our model learns to extract a set of unsupervised keypoints using a keypoint extraction function. It then constructs a graph representation of the scene image where each node in the graph corresponds to one of the keypoints. Similarly, the goal configuration image is also used to obtain the goal graph representation. Next, the forward prediction function learns to estimate the future state of the scene given its current configuration and an arbitrary pushing action vector. The forward prediction function is graph-based. It predicts the future location of the keypoints through multiple rounds of probabilistic message passing operations. For model-based planning using forward predictions, we propose GraphMPC. In GraphMPC, a set of action vectors are sampled. And the optimal action is picked to maximize the similarity to the goal graph. The optimal action is then executed by the robot. For the next time steps, similar steps are followed to sequentially rearrange the objects into the goal configuration. Unlike the prior methods that are extensively supervised using ground truth object state information, our framework only requires raw RGB observations. This is especially useful in real settings where obtaining ground truth object state information is not feasible. Additionally, with our formulation, the scene is factorized into keypoint coordinates instead of object instances. Therefore, it has more generalizability. Lastly, GraphMPC uses graph similarity based on node embeddings. This allows for an accurate action selection to bring the scene closer to the goal scene graph. As a part of our evaluations, we train KINet in simulation by generating random episodes of point-to-point pushing manipulation. We then transfer the learned model from the simulation to the real setting. Specifically, we train KINet using a random subset of 3 YCB objects in simulation and evaluate real robot performance for several different cases, including a similar number of objects, a different number of objects, and extreme out-of-distribution novel objects. We demonstrate that, by learning forward prediction through keypoint factorization, our model effectively repurposes this knowledge and generalizes it to different complex unseen scenarios. Here we show the process of object rearrangement task in a real setting. Although trained on simulation, our model transfers well to the real robot. The robot successfully plans a sequence of pushing actions and rearranges the objects into the goal configuration. Here's another example. For more details and results, please refer to the manuscript. Thank you.